Alright, so today we're going to learn about something that we're going to call antiderivatives. I wonder what that could be. So, you guys might know that there's a course here called differential equations. Don't necessarily be frightened of the phrase differential equation right here. It's not anything close to the material of this completely different course. But fundamentally, that technically is what you would call these sort of questions that we're looking to answer today. We're going to learn some basic integration rules. They're actually just the reverse of the derivative rules, and we'll start off by finding something called the general solution to something that we're going to call a differential equation, and we'll move on to finding again something that we're going to call a particular solution. A lot of new terminology today. Okay, so antiderivatives. An antiderivative is simply the answer to the question. So the antiderivative of 3x squared, let's say, and let's label that with a little f here. The antiderivative of a little f, 3x squared, is simply going to be the answer to the question, what original function that we're going to label big F of x. What original function is 3x squared the derivative of? Right, so up to now, we've been sort of thinking about, in thinking about derivatives, we're basically started with a function, and we're always asking ourselves, what is the derivative of this function? Well, now we're going to ask the opposite question. We're going to start with the function and ask, well, if this is the derivative of something, what was the original? And that's all that antidifferentiation is. But that original function, big F of x, is the answer to the question of what is the antiderivative. The antiderivative, whatever that big F of x happens to be, that's going to be the antiderivative of little f. Okay. Now, having seen 3x squared come up as a derivative several times by now, probably, you might be able to reason out that 3x squared is the derivative of x cubed. You might have, in the unit previous to this, you might have seen x cubed come up a couple times, and when you took the derivative, you ended up with 3x squared. So you might be able to see 3x squared and say, okay, well, that came from x cubed, and you'd be right. So x cubed is, so the answer to the question, to both of these questions, right? These equivalent questions, the answer is that big F of x, that original function that this derivative of 3x squared came from. That big F of x is x cubed, the function x cubed. Although, there's actually going to be a way to start with something and methodically find the antiderivative instead of having to sort of like think back, instead of having to like think back and ask yourself, okay, where have I seen this derivative before? Where did it come from? Let me, flip back through all my memories of all the derivatives I've taken and try to remember where this would have come from. So if there actually is going to be like a simple rule to follow to find these sorts of antiderivatives. Okay. But yeah, so that's the definition of an antiderivative. A function big F is an antiderivative of a little f, and usually you'll be given little f. Don't worry about the interval part. When big F prime equals little f over the interval. But basically that means that big F is an antiderivative if it's what you would take the derivative of to get what you have. The little f that you're given, that you're looking at, is the derivative of something. Right? It is the derivative of some big F. What that big F originally was is going to be what your antiderivative is going to be your antiderivative. So in a way, we're still thinking about derivatives. We're just thinking about them in the opposite direction. All right. Now, in thinking about what the antiderivative of 3x squared was, we came up with an answer, right? X cubed. But you might notice that this would not be the only answer. As you guys know, the derivative of a constant is 0. So just as easily as x cubed would give a derivative of 3x squared, so would x cubed plus 1, or x cubed minus 1, or x cubed plus pi, or x cubed plus 4,999. Like, those would all give a derivative of 3x squared. So this answer that we came up with, right, an antiderivative being x cubed, it's not a unique answer, right? You can tack on any constant to the end of that, and that would also be an answer because the derivative of a constant is 0. So this answer is not unique. There's not one antiderivative. There are infinitely many. Okay, thank God, it's scam, likely. One of these days, someone's going to name their kid Scam Likely. Okay. So yeah, x cubed is not the only answer to this question. There are many antiderivatives. X cubed minus 5 would be an antiderivative. If you took the derivative of that, you would also get 3x squared. If you took the derivative of x cubed plus 97, you would also get 3x squared. So an antiderivative is not unique. They belong to a family of antiderivatives. And if you want to express that, and they're only different to each other by the value of the constant at the end. So if you wanted to express that there's a whole family of antiderivatives that technically, fit the bill or whatever, instead of simply writing x cubed, or even x cubed minus 5, or even writing out as many, constants as you could think of, which you could never technically finish doing because there's obviously infinitely many constants that you could put on at the end there. Instead of doing all that, the simplest thing to do is just add a plus c to the end of whatever you get. That way, you get to represent the entire family of antiderivatives. You can also call it a class or a category. Anything of this form, x cubed with any constant at the end, is going to be a member of this entire family of antiderivatives, x cubed plus c. You don't really have to worry about theorem 4.1. It's just saying that, if you come up with one antiderivative, you can just add any constant or subtract any constant to get another antiderivative. Like, they're all different to each other just by, they're all going to be the same as each other. Their only difference may be, like, whatever constant they have at the end. But yeah, as you find these antiderivatives, you'll be tacking on a plus c at the end just to represent the fact that, the answer to this question of, where did this derivative come from, you'll be adding on a plus c to represent the fact that the original function that you're looking for could be anything, could have any constant at the end. And that capital C there, and it's always going to be a capital C, has a particular name. It's known as the constant of integration. Okay. So what you're going to be doing basically is you're going to be using your knowledge of derivatives to sort of reverse the process of differentiation, right? And once you come up with an answer, you're going to put a plus c at the end just to represent, that whole family. So, for example, you know that the derivative with respect to x of x squared is 2x, right? That's from the power rule. So, if you were to ask, what is the antiderivative of 2x? That's asking, question, what function, big F of x, has 2x as its derivative? Well, the answer to that question, right, is x squared. But not just x squared. You would also want to include x squared plus 1, x squared minus 5, x squared plus 10, x squared minus 9,999. So, the actual answer is x squared with any constant at the end. And because this represents an entire family of possible, equations of, an entire family of antiderivatives, this, with the plus c at the end, is known as a sort of, it's known as a general solution. Right? General as opposed to specific. It's general because, well, it represents the entire family. C can be anything. It's not, C is not any one specific value. C is sort of, all possible values, all possible constants. So it's general, as opposed to being specific. But yeah, that C at the end is known as a constant of integration. And and it's there so that you can capture the fact that there are many possible antiderivatives, infinitely many possible antiderivatives. And it's just there because when you take a derivative, the derivative of constant is 0. So if you go in the opposite direction, like any constant gives a derivative of 0. So if you go in the other direction, there could have been any constant there to start with. Okay. So that answer that we got, that the original function was x squared plus any arbitrary constant at the end, is known as the general solution. And what it's the general solution of is, of course, it's the solution of the question. It's definitely a solution of the question. What is the antiderivative of 2x, or what is the original function that has 2x as its derivative? But stated mathematically, the question that is really being asked is this differential equation right here. Right? There's and I guess back then I called it f instead of g, but technically it's g, I guess. But that differential equation is asking, okay, there's some kind of function g where if I take the derivative of g, that derivative is 2x. What is the original g? Right, that's what that's asking. What is g if the derivative is 2x? Right, and the answer to that is x squared plus c. Yeah. Now, what a differential equation is simply it can involve x and y, but most importantly, it involves the derivatives of a function. So, up to now, most equations that you've been finding solutions for, you're finding, what is the value of x, or what is the value of y, or what is the value of this function, and none of them have really involved derivatives exactly. But now these kinds of equations do, these differential equations. And what you're solving for is no longer, the value of some variable. What you're solving for is a whole equation. Right? The answer to a differential equation is a function. And you're trying to find some original function that satisfies that differential equation. And you want to find some original function, g of x, that satisfies the equation. The derivative of g is 2x. And that function, that answer to that differential equation, is x squared plus c. So other examples of differential equations include, y prime equals 3x. That's basically asking the question, okay, the derivative of y is 3x. What was y? What y gives a derivative of 3x? And we'll find answers to these soon enough. Or, on the other hand, y prime equals x squared plus 1. That's a differential equation that's asking, okay, what y, what function y if you take the derivative, it's going to give a derivative of x squared plus 1. Oh yeah, but, right. So that g of x equals x squared plus c, with that constant of integration at the end that we found, is called the general solution, because it's non-specific. Right, so we're going to find an antiderivative. Right. Now this is equivalent to, and if you want to write it this way, you can. You can write that y prime equals 2. Or, that there's a derivative of some function that equals 2. What is the original function? You probably, I'm sure you've seen some kind of term in all your derivative taking that has given you a derivative of 2. Yeah, so what function, if you take the derivative of it, is going to give you 2 as its derivative? Yeah, 2x. So the general solution to this is y equals 2x. That is the original function that this derivative came from. And that original function is what you're looking for. That original function is the solution to this differential equation. The question of, okay, what gives me a derivative of 2? And with a plus c added at the end, that is going to be a general solution. Because it's not just 2x that gives you a derivative of 2. It's also 2x plus 1, 2x plus 5, 2x plus 10. Those all give you a derivative of 2. So 2x plus c is the general solution. Right? C can be anything, and you can pick any constant to be c, and the derivative of that will give you 2 as its derivative. Yeah. So 2x plus c is the general solution to this differential equation. Okay. Here's a graph of y equals 2x plus c, the answer to that differential equation for various values of c. In particular, we got over here we got y equals 2x plus 2. Here we have y equals 2x. And here we have y equals 2x minus 1. But you might notice that the derivative of all of these is going to be 2. Because the slope, these are lines, so you can tell what the slope of these is. These all have a slope of 2. So they're all going to satisfy the equation, the differential equation. Yeah, they're all going to satisfy the differential equation. The derivative of some function is 2. So that's why it's important to write not just 2x, because if you just write 2x, that only represents one member of the entire family of solutions. In order to capture the whole family of solutions, it's got to be 2x plus c, right? It's got to be that general solution. This isn't actually something that we're going to have to do, but like, you're never actually going to have to write anything in this form exactly. But I'll sort of tell you where it comes from. Just, we're trying to solve the differential equation dy dx equals some function. That's the equation that we're trying to solve. There's some y out there that, if you take the derivative of it with respect to x, gives you a particular little f as its derivative. And you're going to be looking for that y. So if you take this, and this is not technically not a fraction, but if you sort of pretend it is for a second, and multiply both sides by dx, this will cancel out, and you'll be left with dy equals little f of x dx. So once you do that, you can actually take this. Let's say that we have this dy equals little f of x dx, and you throw this little symbol on both sides. Do this thing to both sides. What this left side is going to end up as is the original function y. Whatever this little green symbol does appears to undo, to some extent, whatever this d does, and you end up with just y. And y on the left is going to equal this sort of symbol with f of x on the inside dx. The process that is, I guess, implied by that symbol, so that symbol is known as the integral sign. The process that symbol represents is known as anti-differentiation. Finding the antiderivative is anti-differentiation. And just as commonly, it's something called indefinite integration. And this right here is known as an integral sign. Technically, what it's called is it's literally called a long S. I'm sure you can imagine why. But yeah, this is sort of the notation that we're going to use to depict this sort of antiderivative finding process from now on. And we're going to call that process anti-differentiation. Or, indefinite integration. So how you would read this is, you would read this, y, which is the original function that you're looking for, as a solution to this, to some differential equation. Y is, the equal sign representing the word is, y is the indefinite integral of f of x with respect to x. You can also just say dx, but it means with respect to x. So here we have exactly what we had before. Y is the integral of little f of x dx, right? Or with respect to x. So that variable after that d is going to be known as the variable of integration. For calculus 1, it's pretty much always going to be x, right? So you're always just going to be seeing dx. You won't really see dy or dz or anything like that. That's more for calculus 2 and 3. So it'll pretty much always be dx for you. Now, I don't really expect to be saying this much, but whatever's inside of the integral is known as the integrand. In the same way that something that's being divided is a dividend, or anything that's under a radical is a radicand. Anything that's inside of the integral sign is known as an integrand. But the antiderivative, or the integral that comes out of this, right, is going to be denoted, whatever function the original y is going to be denoted with a big F. Right? And big F is just going to be the, it's going to be whatever, it's going to be one of many antiderivatives that you could get. It'll generally be one without a constant at the end that you're going to get through reversing your derivative rules. And then once you get that, you have to sort of consciously tack on a plus c at the end, just to make sure that you're not getting one, but the entire family of antiderivatives. Okay. So as I said before, if you can remember your derivative rules, you already know your integration rules. One thing to get out of the way before that, though, is just, you don't have to write this down, just know that integration and differentiation are inverse processes to one another. In the same way that multiplication and division are inverse to each other, or that addition and subtraction are inverse to each other, they are sort of opposite operations of one another. And because of that, you know that if you take a number and, let's say you have any number, and then you add 3 and you subtract 3, you're going to get your original number back. You take some number and you multiply it by 2 and then divide it by 2 right after, you're going to get your original number back. In the same way, if you start with some function and you take the derivative and you end up, like right after, taking the integral, you're going to get your original function back. And it works the other way too. If you take the integral of a function and then immediately after you take the derivative, you're going to get your original function back. Just know that, in that sense, they sort of undo each other. Differentiation and integration. Now your actual rules are here, but they are just the reverse of your differentiation rules. The derivative of any constant is 0. That's why you have to add a plus c to the end of every antiderivative you find. The derivative of a constant multiple times x is that constant multiple. The derivative of 10x is 10. The derivative of 99x is 99. If you reverse that, the integral of any constant, the integral of any constant with respect to x is that constant times x. Right? That's just that rule, but backwards. So the integral of 2 will be 2x. The integral of 10 will be 10x. You're sort of asking, okay, well, what would have given me a constant as a derivative? Well, that must have been that constant times x. And that's all that is saying. These next two are less important because it's just they're rules that are just sort of in the background. You guys know that when you take a derivative, you can move around constant multiples however you like. You can do the same for integrals. If you have a constant multiple times a function, you can move that constant multiple into and out of the integral as you'd like. So, for example, in the same way that the derivative of three sine of x you can take that 3 and just take it out of there, and then you can say, okay, well, the derivative of sine of x is cosine, so the derivative is 3 cosine of x. You can freely move constant multiples into and out of the derivative. You can do the same for integrals. So, for example, if you have the integral of 3x squared, you can take that 3 and put it to the outside. Sorry, I should have a dx here. You can take that 3 and put it outside if you like, if that makes things easier. You're just free to move constant multiples around, is all that rule is saying. And in the same way that that derivative rule did, this rule is just kind of fade into the background for you, probably. Like you'll just sort of start assuming that it's a thing you can do, which it is. Same thing with the next one. So you guys know if you're trying to find the derivative of a couple of terms added or subtracted together, that you can find the derivative individually. The same is true for integrals. If you're trying to find the integral of a couple of things being added together, you can just take the integrals individually. And again, that's going to be one of those rules that sort of becomes background noise, and you're not going to remember it explicitly, but you'll just sort of use it like as if it's always been true. Now that last one, that actually is important. That is the reverse of the power rule. So when you take the derivative of a power of x, I'm sure you know by now that the thing that you do is first you multiply the power in the front. And then after that, you decrease the power by 1. In order to undo that, or to do the reverse of that, you would simply do the opposite steps in the opposite order. So when you're finding the integral of a power of x, what you're going to do is instead, you're first going to increase the power by 1. And then divide by the new power. Right, so just sort of comparing these two processes, you can sort of see that this is just this done opposite and backwards. and so multiplying by the power and then decreasing the power by 1. You're going to start, for integrals, you're going to increase the power by 1 and then divide the whole thing by that new power. And I guess also add a plus c, right? There's just one important thing. You can't do this if the power of x you're talking about is negative 1. You can't do it for x to the negative 1, or in other words, 1 over x. Because if you try to do that with 1 over x, or x to the negative 1, well, you'll add 1 to the power, making x to the 0, and then you'll divide it by that new power, which is 0. And so what you're trying to say it is x to the 0 power over 0, which is not defined. So you can't apply this rule if your power is negative 1. If your power is negative 1, that has like a specific integral that I'll probably just like tell you when the time comes. But yeah, those are the integration rules. They're just the reverse of the differentiation rules. And I mean, sometimes it even ends up being the same, like the constant multiple rule right here, and sum and difference rule right here. But for the most part, they're just they're the same rules in reverse. Oh, and to add to that note, right, that n can't be negative 1 because of this whole division by 0 thing, you may have noticed that up to now, you have never gotten 1 over x as a derivative. And there's a reason for that. You've gotten probably every other power of x you can imagine as a derivative, but you have not gotten. There's no way you could have gotten 1 over x as a derivative yet. And there's a reason for that. So here's some, you could say that these are more differentiation rules, but they're not really rules in the same way. It's just sort of recognizing that, if the derivative of sine gives you cosine, well, then all that means is that the integral of cosine must work backwards and give you sine. And same thing, if the derivative of cosine is negative sine, just sort of imagine moving that, taking that negative sign and moving it over here, or getting sine of x by itself. The integral of sine of x must be negative cosine of x. And so you don't actually have to remember these as new rules necessarily, because you can actually, for these two, if you've been remembering your derivatives of sine and cosine in this way, if you've been remembering that, it sort of follows this cycle down as you take the derivative. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine actually brings you back up here, and the derivative of negative cosine is sine. Again. You can actually just take this same thing and reason it in the other direction. Right? If the derivatives are going this way, the integrals, which I'm going to denote with a long s and a little dx there, should go the other way. And as a matter of fact, they do. The integral of cosine, right? You go in the opposite direction, you go up. The integral of cosine is sine. And the integral of sine we should wrap back around, and the integral of sine should be negative cosine. So it's just the same cycle, just working in the opposite direction to differentiation. So you don't necessarily have to remember anything that's exactly new. Okay. All these other ones is just sort of recognizing your derivatives. If you can remember that the derivative of tangent is secant squared, all you do is sort of read that backwards and say, well, the integral of secant squared should be tangent. And, all these have a plus c. Similarly, like all this is sort of asking you to remember is that, if the derivative of secant is secant tangent, well, then sort of reading that backwards, the integral of secant tangent should get you secant. And it's the same for these. If the derivative of cotangent is negative cosecant squared, then the integral of cosecant squared, right, that would have come from negative cotangent, just because you take the negative sign. If you can imagine taking the negative sign from here and just sort of moving it to over here instead, right? Just to get just to get a working positive cosecant squared, then this would be negative cotangent, right? So the integral of cosecant squared will be negative cotangent. And in a similar way, because the derivative of cosecant is negative cosecant cotangent, if you ever have to find the integral of cosecant cotangent, that would be negative cosecant. That's just those trigonometric derivatives, but like read backwards. And it's possible that at this time you're wondering, well, yeah, like those are the derivative rules in reverse, but what's the, what if you wanted to find the integral of secant by itself, or the integral of tangent by itself, or cosecant or cotangent by themselves? Those do have integrals, but you're just not gonna learn them in this course. Particularly because the integral of tangent, maybe, if once we start, if we ever get to learn about natural logs or anything like that. But particularly the integral of secant actually requires it to move from calculus 2 in order to figure out, quite surprisingly. So just for now, the only trigonometric integration rules that you're going to have to remember are just the ones that result from the derivative rules that you already know or already have seen. So these are the only trigonometric integration rules that you guys will really see in this course. Okay. So, let's say you wanted to find the antiderivative of 3x. Or, the indefinite integral of 3x, right? What that amounts to basically is, you're asking the question, okay, what function, big F, what big F function has 3x as its derivative? What function, if I take the derivative, it's going to give me 3x. And, while you could sort of, you could solve it by, like, thinking, okay, have I ever seen 3x as a derivative? now that we know those integration rules, now that we know that we can reverse our differentiation rules to make integration rules, we can actually find this mathematically instead of just sort of, reasoning it out or trying to remember if we've ever seen it before. So you guys remember that power rule for integration. It's just the opposite steps in the opposite order. You're going to add 1 to the power and divide by the new power. Right, that's just the opposite steps to the power rule for differentiation. So this integral, this antiderivative, right, of 3x should be, oh, by the way, I'm just going to note that this is 3x to the first power. If you have x is to the first power, just because of the way that I'm going to be writing this. But if you remember that, then feel free to just sort of write, 3x, squared. But I'm going to be writing it as 3x to the 1 plus 1. Now 1 plus 1 is 2, so I'm going to be dividing by 2. And that ends up being 3x squared over 2, or you can even write 3 halves x squared. And what I mustn't forget is that plus c, because not only is 3 halves x squared an antiderivative, but anything of the form 3 halves x squared plus a constant, that's also going to be an antiderivative. And if you wanted to check that this was true, that this is the kind of equation that gives 3x as its derivative, if you wanted to check this, you could take the derivative of that, c, to get 3x. You can probably just sort of look at it and tell that you do, but if you wanted to check explicitly, what you would do is, take the derivative with respect to x of this 3 halves x squared plus c. So in taking the derivative, to check this, you don't have to, but if you wanted to, you would take this 2, multiply it to the front, and decrease the power by 1. And you'd get that the derivative of this, multiplying by 2 and dividing by 2, cancel out, and you'd just be left with a 3. And the power of x you would have, 2 decreased by 1 is just 1, so you just have x. And the derivative of any constant is 0. So the derivative of anything of the form 3 halves x squared plus c is going to be 3x. And so yeah, that is the kind of function that has 3x as its derivative. That is the general solution, right, to this sort of question of what function has 3x as its derivative. Right, and just to note that in doing this, in following these integration rules, you might have to do similar things to what you have to do when you take the derivative, which is to say that, maybe you have to write radicals as rational powers, or, maybe you have to take some power of x that's on the bottom and write it as a negative power of x instead in order to apply your differentiation rule, or in order to apply your integration rules. That so that a lot of those processes of rewriting and simplifying after you're done are going to be similar between differentiation and integration. We might still have to do this, even when you sort of reverse this process. Okay. And last, we're going to talk about initial conditions. Okay. Well, I guess last for this section. If we get through this, there's going to be a part of section 4.3 that I'm just going to sort of try to blast through, and you guys won't have homework over 4.3, but it contains some things that are going to be important to understanding what we're actually going to be going over on Tuesday. So far, we've been finding these things called general solutions, right? The integrals with a plus c at the end, with that constant integration at the end, because there wasn't ever one particular antiderivative that we were looking for, right? It was always this sort of family of antiderivatives that was able to satisfy, some question. But if you add a little bit of information, that little bit of information being known as an initial condition, if you add that initial condition, then the range of answers stops being, it stops being this family of equations. It stops being the general solution, and it becomes one specific equation, known as a particular solution as opposed to a general solution. Right? Particular meaning like specific. Okay. Right, so you've already seen that this sort of question of, what is the integral of little f, or, what equation has little f as its derivative, you've seen that has a lot of solutions, not just a lot, but like infinitely many, right? Because there are like infinitely many constants that it could have at the end. But if they are all just different by whatever constant they end up with at the end, what that means is that every member of that family is just a vertical translation of each other. Okay. So let's say that we're trying to solve this this integral, this question of, okay, what original function has 3x squared minus 1 as its derivative? We'll sort of see the solution there. But, the way that it would be done, right, is, you're trying to find the integral of 3x squared minus 1 with respect to x. Well, that should be (3x squared), except that I'm going to add 1 to the power, resulting in a power of 3, and divide by that new power. And for that second term, if I have a constant in my derivative, what that means is that that the thing that came from, the thing that -1 is the derivative of, is going to be -1, I don't know why I put a plus, -1x. It is -x that has -1 as its derivative. Alright, so simplifying this a bit, 3 over 3 is 1, so that cancels out, and we're left with x cubed minus x. And plus c, because there could have been any constant on that to begin with, and it still would have given us a derivative of 3x squared minus 1. Okay. So again, this represents a family of potential equations that would give us a derivative of 3x squared minus 1. Infinitely many equations, some of which are depicted here. That top one there is x cubed minus x plus 4, and immediately below that, x cubed minus x plus 3, x cubed minus x plus 2, x cubed minus x plus 1, x cubed minus x cubed minus x minus 1, and so on and so on. And any of these equations would work if solving that integral was all we cared about. So if all we care about is that we have an equation whose derivative is 3x squared minus 1, then anything of that form will be satisfactory. X cubed minus x plus c. And again, that's this is again a general solution. Okay, but let's pretend that that's not all we care about, and in addition to this, we actually care that whatever integral you have, whenever you plug in 2 into it, you get 4. So big F of 2 is 4. When you're given that bit of information is known as an initial condition. It is a condition that whatever equation you have as your answer has to fulfill. That piece of information is enough for you to no longer have a general solution, but to get a particular solution with a specific value of c in order to fulfill that. So there's the initial condition that when you plug in an x value of 2, the function equals 4. Or in other words, it passes through the point 2, 4. Now, if we go back up and look at that family of solutions, right? These are all members of that general family of solutions. You might see that only one of these actually passes through 2, 4. So only one of these, a specific one of these, will satisfy the initial condition that big F of 2 equals 4. And the member of that family that satisfies that initial condition is the member where the constant at the end is a negative 2. So with an initial condition, you can go from having a general solution to having a specific or particular solution, because no longer, with an initial condition, no longer will the entire family of solutions be good enough. Only one member of that family will be. Now, if you want to find what that member is, let's say we have the initial condition, where if you plug in 2, you get 4. How you find that member of that family that satisfies that initial condition is you take your general solution, which is we'll call this big F of x, right? X cubed minus x plus c. What you do is you plug into this general solution and make it equal 4, right? Because that's the initial condition. The initial condition is that when you plug in 2, it should equal 4. So you plug in 2 to to evaluate f of 2, big F of 2. Sorry, that should be cubed. And you make it equal 4. Right, you still write the plus c. So 2 cubed minus 2 plus whatever c is should equal 4. Alright, so this ends up simplifying to 8 minus 2 plus c equals 4. If you combine like terms, that sort of becomes 6 plus c equals 4. And then if you subtract 6 from both sides, you can get that c equals negative 2. So this initial condition actually provides you with enough information to sort of cut your solution down from being this, very vague general family of solutions to a specific member of that family. And so after you find out what value of c satisfies this initial condition, you go ahead and you plug it back. Well, you don't plug it back. Like you make that your c. So the particular solution that satisfies that initial condition up there is x cubed minus x minus 2. This is a particular solution. Right? Particular meaning specific. And a particular solution can only be found if you're given an initial condition to start with. Otherwise, there's not going to be, there's not going to be any information to make your equation specific enough without that initial condition. But if you have an initial condition, there is going to be one equation that satisfies, the initial condition. Okay, so given an initial condition, you can move from a general solution, a family of general, a general sort of family of solutions to a particular solution. But that's only if you have an initial condition. Right, c equals negative 2. Then you obtain a particular solution. Okay. All right. So you want to find the general solution of this sort of this differential equation, right? But really, it's an integration problem. And following that, you want to find the particular member of that family that will satisfy the additional initial condition where, if you plug in 1, you get 0. Okay. So first, the general solution. Okay, you're trying to solve f prime of x equals 1 over x squared. That's just saying that there is some function, big F, where if you take the derivative, you get 1 over x squared. And then it's asking, what is that original function? So what we can do is this isn't necessarily reasoning that you're going to have to do, but basically what's happening is if you sort of put this integral sign and this dx on both sides, integrals and derivatives cancel each other out, so this left side just ends up becoming, regular f, which is what you're looking for, by the way. And the right side turns out to be the integral of 1 over x squared dx. So unsurprisingly, in order to find the original function f, big F, you got to take the integral of this thing 1 over x squared. But anyways, that should make sense, because if 1 over x squared is supposed to be the derivative of this thing, then you should be able to take the integral of 1 over x squared to find out what it is. Okay, but the integral of 1 over x squared, well, that doesn't look too great. Maybe it would be easier to look at if we were to maybe rewrite 1 over x squared. Maybe rewrite it as x to the negative 2. And now it fits exactly the form that we need in order to apply that power rule, which, by the way, is add 1 to the power. Right, this is the power rule for integration. Add 1 to the power and then divide by the new power. Okay, so the integral of this, and, also remember that whenever you actually, do the process of, finding the integral, that the integral sign goes away. Don't take the integral and then also leave the integral sign in there. That's meant to go away as soon as you apply the integration rule. So if you apply this rule, add 1 to the power and divide by the new power, that should give us we'll add 1 to the power. That's going to give us a power of negative 1. So that's what we're going to divide by. And we've applied the integration rule, so there's no integration sign there anymore. And if we simplify that, well, dividing something by negative 1 just makes it a negative. So this will be negative x to the negative 1. Or if you wanted to write it this way, negative 1 over x, right? X to the negative 1 means 1 over x. And not only that, but because we're finding a general solution for, an indefinite integral, we're going to have a plus c. So the general solution for this problem, I have the derivative of something, and that derivative is 1 over x squared. The solution to that is that the original function was negative 1 over x plus any constant. That is the kind of function that is going to give you a derivative of 1 over x squared. So this right here is a general solution. And without an initial condition, that is all you can find. But we do have an initial condition here. We have the initial condition that big F, if you plug 1 into it, it equals 0. So we'll do that. We'll take big F, which, by the way, is, this. And we'll try to solve for what c is. So negative 1 over, we'll plug in 1, plus c, is supposed to equal 0. Okay, well, negative 1 over 1 is just negative 1. Negative 1 plus c equals 0, and that should tell us what c is. Just add 1 to both sides, we can get that c is 1. So from this general family of solutions, the one member that is going to satisfy that initial condition is the member with c equals 1, which is -1 over x plus 1. And so this is the particular solution that satisfies that initial condition. Yeah, so basically to find a particular solution, you find your general solution first. You basically, plug in some values. You plug in a number for x and you make it equal, another number, and you're sort of solving for, the variable c. Is really all you're doing. Yeah. So here's a picture of. So remember that the initial condition is that you plug in 1 and you get 0. So here's a picture of many members of the family, of the general, members of the general family of solutions, -1 over x plus c, right, for varying values of c. And without a initial condition, it could be any of these, and it could be so many more of these that aren't even shown here. But with that initial condition, that you plug in 1 and you get 0, it looks like only one of these passes through the point 1, 0, so only one of these is going to satisfy that initial condition. And the one that does is the member where c equals 1. So that is our particular solution to that initial condition where f of 1 equals 0. So from what we've seen, as far as we know, integration is simply a process to find the solution to a differential equation, right? A differential equation that asks that, hey, I took the derivative of something and this is what I got. What was it to start with? What was the original function that will give me this derivative if I take the derivative of it? That's as far as we know what integration is for. And just, as a reminder, we called those indefinite integrals. Right? We also call them general solutions, like with the plus c and everything. But we also call them indefinite integrals. So we're going to look at something called definite integrals, and it's going to seem like they're for something different, but when we get to 4.4, we'll just you'll see how the two combine in the end. But just if we pretend that we have seen 4.2 and we're gonna sort of look at 4.3, the sort of stuff that we're skipping through by, first of all, skipping 4.2 and skipping part of 4.3, it's analogous to the difference quotient for derivatives, right? So we didn't skip the difference quotient for derivatives, but if you remember, the difference quotient is that whole f of x plus h minus f of x over h. that's like, you know, that is a way to find the derivative without, you know, using your derivative rules. That's sort of how we began finding the derivative before we were introduced to the rules. But you guys haven't used it at all since, and that's because that's like, you know, it helps with understanding what derivatives like are supposed to mean, but it doesn't actually help you find them once you know the rules, like once you know the derivative rules. And this stuff that we're going to skip through is very much the same way. It's just like it's just like the difference quotient. It would theoretically help you, you know, understand something, but it wouldn't actually help you find integrals or, you know, do anything like that. Okay. So the stuff we're basically skipping is a bunch of area finding. So the idea behind this stuff that we're skipping is that you can find the area sort of under a curve, or, you know, in other words, between a curve and the x-axis, by making a bunch of rectangles and then finding the area of those rectangles, because rectangles are easy to find the area of. You just take the base, take the height, multiply them together, and that's the area of the rectangle. And so you can see here that, let's say you're trying to find the area under y equals square root of x, right? The square root function, maybe just from 0 to 1. You can sort of see here that with 1, 2, 3, 4, 5 rectangles, it's not, you know, it's an approximation, yeah. But it's not that great of an approximation because, like, there's all this part of the rectangles that, like, goes past the actual function, and so you're going to overestimate, you know, if you use these rectangles, you're going to overestimate the area by, honestly, quite a fair bit. But the idea is that if you form areas in this way and you increase the number of rectangles, you're going to get a closer approximation. So if we sort of pretend that we're doing the same thing, and let's say we go to 1 or whatever, you know, we start at 0 and go to 1. But we increase the number of rectangles. You know, sort of lining up these rectangles, you know, lining up the corner of these rectangles with the actual graph itself. You know, notice that the upper right corners are always sort of on the graph. You can sort of see that if the number of rectangles goes up, your approximation is a little better. And so the idea is to increase the number of rectangles by so much that that it becomes such a good approximation that it literally gives the exact area under the curve. And the number of rectangles that you need to do that is infinitely many. And if there are infinitely many rectangles, then, you know, of course they have to be infinitely thin. You know, until each like there are infinitely many rectangles of width 0, and that becomes kind of weird to do unless you have limits, which, you know, we would use, right? We would actually try to find this a formula for the area as the number of rectangles approaches infinity and the width of the individual rectangles approaches 0. That's what we would, you know, have to do if we were actually doing this. But, you know, that's the idea behind what we're trying to do. We're trying to find the area under a curve. Right? And so there's all this stuff involving, like, summations and, you know, limits as the number of rectangles goes to infinity that we're just going to sort of skip. And anyways, the area under that curve is exactly 2/3 square units. which also means that, if the area under here is 2/3, the area here must be 1/3. Right, subintervals, Riemann sums, width of a rectangle, partitions. Okay. So, at this point, we would basically be saying that this thing that we're finding, this area that we're finding by, taking the limit as the, number of rectangles goes to infinity and the width of the rectangles goes to 0, this area that we're finding can be represented in this format. Now that looks very similar to what we just did, the difference being that there appears to be a number here and a number here. An A down there and a B up there. And what those are the number A is the lower limit of integration, and the number B is the upper limit of integration. Those are our limits of integration. And what that's going to mean is A and B are x values. They are x values that you are finding the area from and to. So let's say that you had some arbitrary curve that we're going to call f of x. Okay. If you wanted to find the area under this curve, of course you'd have to keep it between two particular x values, because this curve just it's not like it stops. It's not like it has a finite area under it. You would say that you want to take the area from A to B. Right? So from an x value to a different x value. So what you would be finding when you say that is the area under this curve, between this curve and the x-axis, specifically. And the notation you use to represent that is that you say that you're finding the definite integral from A to B of the curve f of x dx. This is the area it's the area between f and the x-axis from x equals A to x equals B. And as for why it looks so similar to the thing that we just did, only with that extra A and B, as far as we know, that is coincidental. It's not, but we don't know that yet. Okay, so this is just all, this section is just going to be all about finding area, and with that A and B there, this is known as a definite integral, because it's like, it's being defined from some x value to another x value. Right? With that A and B, it's known as a definite integral. Without the A and B, what we just got finished doing, it is known as an indefinite integral. Okay, but a definite integral it just means the area under the curve described, inside. Okay. Blah blah blah. 2x. there's this whole process for finding this, like later, even if you learn this later, you would just throw it away in favor of those integration rules from earlier. Okay. So a definite integral can be thought of as an area, but you have to make sure that if you're going to think of it as an area, that you think of it as a signed area. Just meaning that it can be negative or positive depending. In fact, when you're finding the definite integral, the places where it's below the x-axis are actually going to be equivalent to a negative area. The definite integral is the signed area between a curve and the x-axis, curve f of x, and the x-axis from x equals a to x equals b. So in this case, what all those steps that you just saw were in order to find the definite integral from -2 up to 1, from x equals -2 to x equals 1, of the function 2x. And what that equals actually ends up being -3, which is a little bit weird if you think of an area. But if you think of it as a signed area, then it becomes a little more apparent what's going on. So here's -1, here's -2. Okay, so it sort of collects the area on in between these two x values, -2 and 1. And because this is below the x-axis, it's actually going to be so first of all, notice that this is a triangle. It's a triangle with a base of 2 and a height of 4, right? So if you just sort of think about the area of a triangle, it's going to be 2 times 4, which is 8, cut in half. So this triangle has an area of 4, except that it's below the x-axis, so it actually has an area of -4. Now this part, this is above the x-axis, so it should be a positive area. And this triangle has a base of 1 and a height of 2. So 1 times 2 is 2, cut that in half to get the area of the triangle. That's going to have an area of +1. Now if you add this negative area, -4, and this positive area, 1 together, you're going to get the value of the integral, -3. And later on, when we get to section 4.4 on Tuesday, we'll find an actual, way to use our derivative rules and not use rectangles in order to find the value of these definite integrals. And we won't have to use, geometric formulas either. No noticing, hey, this is a triangle, 1/2 times base times height. But that's what a definite integral means. That's how it's interpreted. Right, that's just sort of the same picture as before. Yeah. So the area between this parabola and the x-axis is given by the definite integral from an x value of 0 to an x value of 4 of this parabola being 4x minus x squared. That's why it's inside the, that's why it is the integrand. So the integral from 0 to 4 of 4x minus x squared, that's going to give the area between this curve and the x-axis from 0 to 4. Okay. all this stuff is doing is basically, I mean, you can, I guess, look at it later if you want, but it's meant to solidify the concept of an area because this is going to be a rectangle, and you use a formula for the area of a rectangle to find it. This is going to be a triangle, this is going to be a half circle, a rectangle, a trapezoid, and a half circle. So it's just saying, it's just giving you a couple of techniques to get around actually, doing any math and only doing, doing any calculus and only doing geometry. All right, but the idea behind an integral is that you're sort of collecting the area under a curve, or collecting the area between a curve and the x-axis. Okay, now these are the only two important things. If you think of integration as a process of area collection, from some x value going to another x value, some interval. If you start and stop at the same number, if you collect the area from here to also here, you're not going to be collecting any area at all. So any integral that goes from a to a is 0. Right, so if you take an integral and it goes from 1 to 1, well, it goes nowhere. It collects no area at all. Same as if it goes, if you take the integral from 5 to 5, or the integral from 4 to 4, there's no area collected at all. Second, if you switch the order of your limits of integration, like let's say you go from 1 to 2 and you collect a certain amount of area, if you switch those limits of integration and you go from 2 to 1, essentially going backwards, you're going to get the negative of what you got going forwards. So like let's say you're taking the area from 1 to 2, you found out there's an area of 5. If you switch your limits of integration and instead start at 2 and go backwards to 1, the value of the integral that you're going to get will be negative 5 instead. So just if you switch your upper and lower limits of integration, you're going to get the negative of what you got before. Okay.